Hi, now let's continue with introducing generative adversarial networks. So what is a GAN? What is a generative adversarial network? Well, first of all, it's a generative model, which means that with it we can generate novel inputs, images, for instance, that they never existed. It's adversarial. It's a model which is adversarial, which means that it learns by contrasting against somebody else, some adversary. In this case, another neural network. And it's a network, which means that it is modeled as a neural network. It can be implemented as any neural network, and we can easily add modules. We can easily use backpropagation. What is the intuition behind GANs? We can think of it as a situation, as a game, so to speak, between two parties, the police and the counterfeiter. The police tries to detect fake money as reliably as possible, and the counterfeiter wants to make fake money which look as real as possible. Now, if we let these two parties play against each other, we can easily imagine that the police will force the counterfeiter to improve the fake money that they generate, and vice versa. The better the money that the counterfeiter makes, the better the police has to become to detect it. By the end of it, both the police and the counterfeiter will be in an equilibrium. Specifically, the final solution, the convergent solution, would resemble something like a Nash equilibrium. What does a GAN architecture look like? Well, it has some very common elements, as we've seen so far, especially for generative models, but also some distinct differences. First of all, it comprises a generator network, which receives as input a noise variable z, and returns as outputs samples from the input space, so like for instance images. Then it also comprises, it also contains a discriminator network which returns a binary output variable and receives as input samples, for instance images, and this can be either generated by the generator or can be obtained by our training data. The discriminator will return a +1 if it thinks the input is a real image, and 0 if it thinks that the input is a fake one. What is important to emphasize here is that GAN has no encoder, unlike variational autoencoders or Boltzmann machines. We cannot learn a representation for a given image X. It's not like we can, given a particular input, we can return a latent representation. No, that's not the case. Also, we cannot compute the likelihood of a specific data point, at least not in the original GAN formulation. At test time, we can only generate new samples, new input samples, for instance, new images. The generator network can be any differentiable neural network. There is no invertibility requirement. There are no approximations needed or normalization constants needed to be computed. This allows for much more flexible modeling. The generator network can be trainable for any size of z, and as a noise variable z, as a stochastic noise variable z, we can use various density functions. We're not restricted to either the normal or the uniform distribution. We can use anything we want. For the discriminator network, again, it can be any differentiable neural network which receives as inputs either real images from the training set or generate images as returned by the generator. Usually it receives a mix of both, so a mini batch will contain half real images from the training set and half generated images from the generator. And then the discriminator must recognize which are real and which are fake. This means that, during training, we do not explicitly give any label or any information to the discriminator as to per which of the samples in the mini batch are real or generated. We send them both to the discriminator, and then the task of the discriminator is to figure out what is what. Regarding implementation, the discriminator and the generator can be any neural network. The generator looks like an inverse discriminator, and we're very flexible in the way of designing it. So as a pipeline, we first have input noise z, and we pass this onto a differentiable function g, standing for the generator, and we sample a new data point, a new image, for instance, from our generator. Then we pass this to the discriminator. At the same time, we sample x from our input data, so this is a real image, whereas this is a generated one. And then we pass this also to the differentiable discriminator. Then the discriminator tries to detect this as a real image, whereas in the case of the generated image, the discriminator tries to push the generated inputs to be receiving a likelihood next to 0, whereas the generator tries to do the opposite. That is, it tries to confuse the discriminator to assign high likelihoods to the generated inputs. So regarding learning objectives, with GANs, it's not obvious how to use maximum likelihood. It's not that it's not possible, as we will see, but it's not obvious. It's not like the first thing that comes to mind. Because even if we take the output of the generator, how are we going to train the discriminator? So even if we were to use these as our outputs to return some likelihood, this part of the network would still be out of the loop. But even then, how do we even know whether an input X is good enough or not, if it's real or not? Our discriminator is also not trained, it's also random, so it cannot really recognize yet which samples, which inputs are fake or genuine. And remember here that we have no encoder, so no target to compare against. We've got no way of, for instance, doing some sort of regression here. A first approach to defining a learning objective is to have a minimax game definition. So for this simple case, we've got a zero-sum game where basically we ask the generator and the discriminator to have equal losses, and the lower the generator loss, the higher the discriminator loss. This yields a symmetric definition which can be reduced, which can reduce our learning objective into this simple equation of v being equal to minus the cost of the discriminator. Now, in this case, when d of x equals to 1, the discriminator believes that we have a true image, and when the g of z as input to this discriminator is assigned a likelihood of 1, then the discriminator thinks that the g of z is a true image. With a minimax game, the learning stops after a while, because as training iterations increase, the discriminator improves, and then the preceding generator has vanishing gradients. The equilibrium in the end is a subtle point of the discriminator loss, and the final loss resembles the Jensen-Shannon divergence. The min-max game is amenable to easier theoretical analysis, and this is the main practical value it has. But other than that, it doesn't really work. It doesn't really converge to meaningful solutions. The heuristic non-saturating game is another learning objective, another definition of the learning objective, which is the most widely used. In this case, our discriminator loss is basically, here the equilibrium is not describable anymore by a single loss. So the discriminator maximizes here the likelihood of detecting the real images as real, right? And it also maximizes the likelihood of discovering the fake sample. So 1 minus d of g of z should be high. This means that the d of g of z should be close to 0. So when we receive fake images in the discriminator, then the discriminator should assign low likelihoods to it, which means that this term gets maximized. On the other hand, the generator loss focuses only on confusing the discriminator. So when we input a generated data point onto the discriminator, the generator loss wishes the discriminator to assign a high likelihood to it. This means that the generator doesn't care if the discriminator gets confused with the real samples. It only cares whether it is confused with the generated ones. This objective is heuristically motivated, and the generator can still learn even when the discriminator successfully rejects all the generated samples. We can also modify the gun for maximum likelihood. And in that case, the discriminator loss remains the same, but for the generator loss, we activate the output of the discriminator by an inverse sigmoid. It can be shown that when the discriminator is optimal, so when the gradients of the discriminator with respect to its parameters are close to 0, then the generator gradients matches that of the maximum likelihood objective. It's interesting to compare the different generator losses, how their curves look like. So a very important observation is that when the discriminator here, in this area, we have that the discriminator assigns very low likelihood to generated samples, right? So our generated samples get very low scores for discriminator. So it means that the discriminator is able to discover accurately that these are indeed fake samples. Now we see that our generator loss for the minimax game is basically a flat curve, which means that the gradients will be very small. So when our discriminator does a good job, when it has converged, then there are basically very small gradients towards the generator, which means that the generator cannot improve. There can be no learning no more. At the same time, the maximum likely host, or like in reverse, in contrast, the maximum likelihood cost in the range of d of g of z being high, so when it's actually when the discriminator is actually confused, generates gradients mostly from the good generations. So all gradients are from high, from few samples only, and this means that we've got high variance and unreliable gradients, right? And why from good generations? Because these good generations are the ones that confuse the discriminator. So this means that the gradients might be having high variance and might confuse convergence. At the same time, the heuristic loss yields good generator gradients here when the discriminator is too good, so what we desire, while it generates very small gradients when generator. It generates good gradients when the generator is not that accurate. So in this area, while it returns very small gradients when the generator is very good. So what is the optimal discriminator? The optimal discriminator can be determined to be basically equal to the probability of the data over the probability of the data and the model. This is, in convergence, this is what the discriminator would optimally achieve. And this makes sense. This means that it confuses basically the data and the model with the according ratio. And estimating this ratio with supervised learning is the key. So here we're having a supervision loss, a cross-entropy loss, and by the end of the discriminator. So this is very important. Graphically, this is how it looks like. So in the beginning, our generations will be gathered in a very particular corner of our space, and we're going to generate a lot of similar x's. This means that in the beginning our discriminator is very noisy, so it's going to receive a gradient, and in the next step it's going to correct itself, so it assigns low likelihoods on these generations and high likelihoods there. Right, so this makes the generator, the discriminator more accurate. And in return, this pushes the generators to move the generations more to the left, closer to the actual data distribution. And by doing this multiple times, we end up with a generation that looks like the data distribution, and the discriminator can at best have a 50% chance of discovering whether samples are real or not. So why is this the optimal discriminator? Well, we can write down the loss, the cross-entropy loss, like here, and if we minimize the loss with respect to the discriminator, and ignore the integral because we sample anyways over all possible x's, then we obtain this function of a times the logarithm of x plus b times the logarithm of 1 minus x, which has its maximum at the location of a over a plus b. So our optimal discriminator is indeed the one which has the probability of the real probability of that input over the sum of the real probability and the model probability for that input. At optimality, the generated probability, so the model probability, will converge towards the real one. So our optimal discriminator will then have 50% chance of success, and our optimal loss will be minus 2 times logarithm of 2 after replacing this in the equation of the loss. For the precise steps, this is a great block with also great intuitions from Lin and Wang. It can be shown that GANs have very close connection to the Jensen divergence. So if we expand the Jensen-Shannon divergence for the optimal discriminator, we can see that basically the Jensen-Shannon divergence has a linear relation with the loss of a generative adversarial network. Specifically, the loss of a GAN is 2 times the Jensen-Shannon between the real distribution, the probability of the real distribution, or the real probability density function, and the model probability density function minus a constant. And what is even more interesting, or well, noteworthy anyways, is that we know that for the optimal case, our loss would be 2 times the logarithm of 2. So basically, this if we plug this into the above equation, we obtain that the optimal Jensen-Shannon is between the two distributions is 0, which checks out. It means that at optimality we're going to have exactly the same density function for our real distribution and for our generated distribution. So basically in this slide we saw that our generative adversarial networks are minimizing something that looks like the Jensen-Shannon divergence. In fact, the rescaled version of the Jensen-Shannon minus a constant. Now, why is this important? Does the divergence make a difference? We sort of discussed this in the lecture of variational autoencoders, and indeed there is a difference. So the Jensen-Shannon divergence is symmetric, whereas the KL divergence is not. Right, because the Jensen-Shannon divergence is basically a weighted sum of the KL, the forward and the backward KL divergence. So the forward KL divergence of the real over the compared to the real plus the model over 2, and the backward divergence comparing the model distribution with the real plus the model over 2 distribution. Now, since the Jensen-Shannon is symmetric, while the KL divergence is not, has some repercussions. So the KL divergence is not symmetric. So which density function will be placed in the leading or the following position plays a role. If we have the forward KL, it means that we put high probability everywhere that the data occurs. And the forward KL is basically what we saw to be the maximum likelihood objective. So the forward KL optimizes the maximum likelihood objective. The backward KL divergence assigns low probability wherever the data does not occur. So it picks a mode and therefore underestimates variance. So for the rest of the space, it assigns 0 density. So we can say that the backward KL is 0 forcing the learned model. It forces it to place zeros wherever it cannot be confident enough and avoid areas in general where P of X is 0, because that could actually penalize the divergence too much, can make the divergence grow very large. So some general observations is that GANs are designed to deliver good generations, and with the GANs we don't have encoders, so we've got no latent variable model anymore. We've got no representation for a given input X. We cannot use this, for instance, for downstream tasks like classification. With GANs, we do not write also the densities explicitly, and regardless, we can do generations, but we cannot easily do inferences, compute conditionals, marginals, and estimate other statistical quantities that might be needed for us. However, we can do very good generations. Regarding the training procedure, generally SGD, an SGD algorithm of your choice is well advised. Generally, Adam Optimizer is a good choice. Use 2 mini batches simultaneously, one containing real training data, the other one containing fake generated examples from the generator. And an optional tip that often seems to improve training is to run case steps for one of the players, for instance the discriminator, for every step of the other player, for instance the generator. Thank you.